So hi everyone, so my name is Tsun-Yu, and today I'm going to present our work that is practically boosting the processing performance of BFS-like algorithms on semi-external graph system via IO-efficient graph ordering. And many kinds of graph systems are proposed in the field. And among all of them, the external-based graph system provides a low cost and high scalability to process graph in a single machine with the help of the storage. And the external based graph system can be further divided into a fully external and the semi-external graph systems. So the fully external graph system stores both of the vertex and edge data in the storage and load only the necessary part into memory during runtime. And this kind of graph system are very cheap for only requiring a small size of memory. But the performance is often undesirable for incurring many random writes to the storage. And the semi-external graph system choose to keep the small size of vertex data in memory and store the larger size of edge data in storage. So all the random update can be directly absorbed by the memory, making the semi-external graph system a cost-effective solution for the graph processing. And although semi-external is more efficient than the fully external, their performance is hard to reach optimal for some graph algorithms such as the BFS-like algorithms. So the BFS-like algorithms are an important set of graph algorithms which are built based on the recursive traversal, which is also known as the vertices. So the BFS-like algorithms only activate a subset of the edge data at any given time. And moreover, due to the irregular structure of the neural graph, and it's challenging to predict which vertex is active. And therefore, the access pattern to the edge data is often sparse and random. And the below figure shows an example of running the BFS algorithms on the semi-external graph systems. And all the active edges will be loaded into the cache for being processed by the graph algorithms. And because we can only access the storage device using the granularity of blocks or pages, and the BFS-like algorithms has a sparse access pattern. So we can observe that in this example that a larger portion of the loaded page will not be used by the graph algorithms, which will waste a lot of IOs. So to alleviate the poor performance of BFS algorithms, that the existing work looks for the opportunity of the processing optimizations. And the first technique that I propose is the neighborhood ordering, which is also known as the unordered. So since the neighbors of a vertex will be accessed together in the BFS-like algorithms, so the goal of an unordered is to place the neighbors of a vertex with close vertex ID. So by doing this way, that the attributes of the neighbors will be stored closely in the storage. And the unordered will repeat this tag starting from the highest integer vertex because the high integer vertex is likely to be accessed early in the BFS-like algorithm. And by doing so, that the unordered helps to improve the locality of access to the edge data. And the second technique that I propose is that it discovered the traditional patch cache management for managing the loaded edges is inefficient for the BFS-like algorithms. So they leverage the concept of the static cache and propose the greedy vertex selection to select and fill the static cache. And the general idea of the GVS is shown in the below figure. And we can observe that if V is currently accessed, then the edge list of the vertex 1, 2, 3, 9 will be needed in the next iteration. So in this example, we can see that the vertex 1, 2, 3 are stored in the same page A, but the vertex 9 is stored in a different page B. So accessing the page B during runtime is inefficient because a whole page will be loaded, but only a small portion of the page is needed. So the GPS will try to detect this kind of vertex and preload the attributes of the vertex 9 inside the static cache before the graph processing, so that during the runtime, we only need to load the page A. And to illustrate the effectiveness of this design, we use the IO efficiency to measure the effectiveness. So IO efficiency is defined to be the ratio of the number of bytes required by the BFS-like algorithms to the total number of transfer bytes. And as shown in the below figures, that an IO request with the high IO efficiency means that the more data in the loaded page will be used by the algorithms. And the low IO efficiency means the opposite way. So we use IO efficiency to measure it because that the BFS-like algorithms often hold two features. The first one is that the BFS-like algorithms show higher demand for IO than computation. And the second reason is that the modern semi-external graph systems typically overlap the IO with the computations. So due to these two reasons, that the BFS-like algorithms are generally IO intensive. So higher IO efficiency means that they can perform in a better way. So we measure the performance of an order and GVS in the slides. And as shown in the right figure, like we fix the size of a traditional cache and range the size of static cache from 0% to 40% to the of the edge data. And we can observe that an order is ineffective as it only has IO efficiency of 42%, which means that almost 60% of the loaded data will not be used. And on the other hand, the GVS helps the performance as the size of static cache size increase. But unfortunately, that the GVS require a heavy preprocessing cost, which is shown in the below table that is marked with the red rectangle. And such high time complexity in the preprocessing might lead to limited predictability for spending too much time on the preprocessing compared to the improvement that the GVS can bring. So this work proposed IOE-Order, which is an ordering to optimize the grid layout with two goals. So the first one is to better improve the locality of access to the edge data, and this will be achieved by the BFS ordering. And the second one is to facilitate the pre-caching with the low processing cost, and this will achieved by the autocomplete. And the below figure shows the flow of the entire graph processing. And to begin with, the original graph will be optimized by the BFS ordering and then the autocomplete. And the next step is that the pre-caching step will fill the static cache, and finally we will run the graph processing. So to improve the locative access, that the goal of our ordering is to know which vertex are likely to be accessed together. And for this purpose, we follow two intuitions. So the first one is that the high integer vertex is likely to be visited earlier than the other vertex. And the second intuition is that the vertex which are recursively connected to the high integer vertex are also likely to be accessed early. So based on this intuition, that we propose the breadth first degree second ordering, which can help us to capture this relation. So as shown in the right figure, that the BFDS do the BFS starting from the highest integer vertex, as it has the higher probability to be accessed early. And next, we will assign the consecutive IDs to all its own neighbors. And within the set of active out neighbors, we sort them based on the integrity. We sort them based on integrity, and then keep assigning new ID to our neighbors, starting from the highest integer vertex. So the procedure of this reordering will keep continuing until the BFS converges. So the next step of our reorder is the autocomplete, so which is proposed to further facilitate the pre-caching. And in particular, that based on the graph that is reordered by the BFS, the autocomplete further create multiple bins in the graph layout based on the out degree of each vertex. And the right figure shows the idea of out-degree bin by separating the graph into two bins, which are the large out-degree bin and the small out-degree bin. The edges in the small out-degree bin can be sequentially pre-cached in the static cache, and we will load the edges in the large out-degree bin during runtime. So the out-degree bin has three advantages. So the first one is that accessing the large out-degree bin enjoy higher IO efficiency, as there's no small vertex inside the bin. So the second one is that given the fact that a BFS-like algorithm can activate each vertex the same amount of times, so the pre-caching more vertex inside the static cache can help to prevent issuing more IO requests. And the third one is that unlike the traditional method, which directly pre-cache the vertex, the bin separate the pre-cache data and unsorted data. So under this kind of a bin strategy, loaded page will not contain the package data. And this is possible to further improve the utilization of the loaded page. But in the real world, that a different machine may have a different available memory for the static cache. So for better practicability, that autograph bin will create multiple bins in the graph layout. But we discovered that the bin size is important for the overall performance. And that is to say, if the bin size is too small, then the structure of a BFDS order graph could be destroyed. So it will make the ordering less effective. But if the bin size is too large, then we could fail to catch the critical edges. So we propose to configure bin size following the exponential decay of the edge data size, which is shown in the below figures. So the bin of a large out degree are kept inside in the left-hand side, and the bin of the small out degree are kept in the right-hand side. So the pre-catching is easy and efficient by sequentially read the edge data from the right-hand side according to the size of the static cache. And based on our evaluation, that the exponential decay bin size is appropriate for the large scale of processing, as it performs well with or without the static cache. And we implement IOE-Order in the C++ and evaluate it using Graphene, which is an open source and state-of-the-art internal web systems. And we run our experiment on the HP server, and all graph data is stored in the Samsung A60 EV01 TDSD. And in the following experiment, where we vary the size of static cache from 0% to 40% to see the effectiveness of the ordering and the pre-catching. And the traditional cache is size of the cache is fixed to be 5% of edge data. And beside an order, we further evaluate two ordering, that is a random order and the integrity order. And the integrity order is to reassign the vertex ID based on the integrity of each vertex. And for the vertex selection, we further evaluate the out degree bin vertex selection. And this will leverage the out degree information to pre-catch, but it doesn't have the optimization of the bin strategy. And this slide shows the overall comparison, and in particular that we test on 3 BFS-like algorithms, which is the preferred search, the BFS, the weakly connected component, the WCC, and the all pairs shortest path, the ADSP. And the x-axis indicates the size of static cache, and the y-axis shows the processing time. So since the trend of the IO efficiency is similar with the trend of the processing time, so we skip the figure of the IO efficiency here in this slide due to the time limitations. And for the result, we can observe that the random order performed worse, and then the integrity order, and then the unordered. And the IOE-Order, which is the pink line, performed the best compared to all the other designs, no matter with or without the static cache. And this is because the BFDS provide better locality of access to the edge data, and ultimately mean further improve performance with the static cache size by leveraging the out degree information and the bin structure. And this slide shows the pre-processing cost where all times are measured in seconds. The static cache in this slide is assumed to be 20% of the edge data. So we can observe that although the BFDS generally require more time than an order, the out-degree bin is much faster than GDS. So therefore, that if we sum all the processing costs, the overhead of IO-Order is much faster than an order plus GDS. And to further discuss the impact of IO-Order on the non-BFS algorithms, that we further evaluate 2 popular algorithms, which are the PageRank and the K-code. And these 2 algorithms represent 2 completely different access patterns. And PageRank will repeatedly process all vertices, and the K-code will selectively remove the vertex in order to return a subgraph that all the vertex in a subgraph has a degree that's larger than K. And for PageRank, we can see that the IO-Order delivers a similar processing time as in degree ordering and unordered. As for the K-core, that IO-Order perform better than the rest of the ordering because the out-degree bin create a good locality of access for the K-core. And because the out-degree bin store the vertex of a similar degrees together, this will create a good locality for removing the vertex of degree that is smaller than K. So in conclusion, that IO-Order combines the ordering and the pre-catching via optimizing the graph layout. And the IO-Order is proposed to practically boost the processing performance of BFS algorithm on semi-external graph systems. And for runtime performance, that IO-Order can improve the unordered plus GVS by 18.8% on average. And for the processing cost, that IO-Order is averagely 32.9 times faster than the unordered plus GPS. And this concludes our presentation today, and thank you for your attention.